All right, we're gonna do 10.9. This should be pretty short. At the end of the notes, there are a few examples that don't necessarily have to go with this section, but I'll just leave them. I'll fill them out in the notes so that you can have them, but I'm not gonna include them in the video in case you want to try them. So basically, what we're gonna do now is figure out essentially how close of an approximation is our Taylor series as we do it. Is it going to give us an accurate answer out to 1 decimal place, 100 decimal places, or what is it? So we have to come up with an idea of how to look at that. So if you remember back in the day, there was a mean value theorem, which basically said that if we were between 2 points on a graph, and that somewhere between there, assuming it's a nice smooth continuous graph, we will have a point on that graph where the slope of the tangent line at that point is actually going to be equal to the average, or the slope between the beginning point and ending point. And so we're doing something kind of like that here. Basically, what we're saying is that if we look at a whole bunch of derivatives of something, that however many steps is what this theorem is saying. It's basically saying if we go out 100 steps, then there's a way that we could go out to the 101st step, and then we could get a value that was inside the interval between where we were looking, such that it could be added on to the end, as part of that 101st step, that would actually then make it completely equal to the beginning. And that extra little part, we're going to end up calling that the remainder. It's like the leftover part. It's how far off, if we do 5 terms, it's going to be how far off those 5 terms are from the actual exact value of the function we were looking at. And so in this part, this would be f of b equals f of a plus f prime of a times b minus a plus f double prime of a over 2 factorial times b minus a squared. So we're just doing the regular series here, plus dot dot dot, plus f the nth derivative of a over n factorial times b minus a to the n. And then normally we could just keep going here because it's an infinite series, but what we're going to end up with is this extra little part here at the end, which I might change colors for, which will be f to the n plus 1 derivative, and then evaluated at c. And c is that point that's between a and b. There is somewhere in between them. There is such a point that exists, that when we get this, and we find that value of c, we can do this, n plus 1, and we can actually stop there. And they're going to be exactly equal. And so essentially this little part here at the end kind of tells us how much our Taylor series is off if we go n number of terms out. And so it's just about finding that. And so what we can do first is use this to decide if a function converges, and it's going to converge if that remainder part of that basically goes to 0 as we take n out to infinity. So a Taylor series is going to converge if the limit as n goes to infinity of f to the f of the n plus 1 derivative, I'll say that right, over n plus 1 factorial times x minus a to the n plus 1 equals 0. So if that occurs, then we're going to end up being that. Now, one of the things we're going to do up here with this Taylor series, what's most common to do to find this remainder, is actually to actually fix a point A. So typically, you're going to fix A, like make it 0 or something to some number, and then you're going let b just be some variable like x, and we're going to basically use it by that. So let b equals x, and it can vary. Okay? And so we're looking between a and some x. Kind of like if we integrated from a to x, if you want to think of it that way. So next, let's look at an example here. And so here we're going to look at the series e to the x. Now, using the Taylor series expansion of this, right, we get that e to the x equals 1 plus x squared over 2 plus ... plus x to the n over n factorial plus, and then we're going to have something here. We'll have e to some value c that's in the interval between 0 and x, and then it's going to be over n plus 1 factorial times x to the n plus 1. Because remember, we're letting b go to x, right? We're letting b go to x. And so we've got that here. And one of the things you need to remember, this was from back in chapter 1, or not chapter 1, section 1, I believe, section 1 or 2. But x to the n over n factorial, that'll go to 0, which means that x to the n plus 1 over n plus 1 factorial will go to 0. So keep that in mind here. As n goes to 0, that'll happen. So we have a couple of options here. First, we can have x being a positive number. If x is positive, then what we end up with is e to the c over n plus 1 factorial is times x to the n plus 1 is going to be less than e to the x times x to the n plus 1 over n plus 1 factorial, which should make sense. All right, because c has to be less than x, and so that'll end up being less than it. And then this will go over here as n goes to infinity. This is this right here, this circumstance. This will go to e to the x times 0. Remember, x isn't going to infinity, n is going to infinity. X is just some number. We just haven't chosen it yet. We might choose it to be infinity or something like that, but we haven't chosen it. So at this point, it's some number, and it's any number that's positive. And so e to the x times 0, of course, that equals 0. So that's good for that one. For x being negative value, right, then what we end up with is e to the c over n plus 1 factorial times x to the n plus 1 is less than e to the x times x to the n plus 1. Well, sorry, no, I'm miswriting that, sorry. It's less than the absolute value of x to the n plus 1 over n plus 1 factorial, and that's in parentheses, and that goes to 0 as well. So that's good, that works for us there. And at x equals 0, x is actually 0, it's not positive or negative, it's 0, then e to the c times x to the n plus 1 over n plus 1 factorial is going to equal 0, because it's x is 0, over n plus 1 factorial, and that goes to 0 as well. And so since they all go to 0, it goes to 0 for all of these x's. Therefore, the Taylor series generated by e to the x converges to 1 plus x squared over 2 plus ... x to the n over n factorial. Everywhere on negative infinity to positive infinity. And basically what that means, we can say, is that they're going to be actually equal to each other, not just approximate, not just there, it's equal for any x. So that's pretty good. So let's go ahead and take a look at the next part. We can estimate the error that goes along with this by picking a value that is going to end up being inside of it. This is called the remainder theorem, and you should take a look at it. It's on page 643 remainder theorem. I'm going to just kind of sum it up for you here. But the idea is that this remainder that we were coming up with back over here, I'm actually going to go ahead and label it this, Rn of x. That's what that is called. I'm talking about this remaining part over here. That remainder part, Rn of x, the absolute value of it, is going to be less than or equal to some value m times x minus a to the n plus 1, the absolute value of, over n plus 1 factorial. And this value m basically just has to be a number where all of your function values are less than it. And since we're getting something that, you know, is telling us that it's going to be less than that, our error is going to be less than that, really, I mean, you can pick any number you want that stays larger than your actual function values or your function value derivatives at that point. So what I'm saying is m is greater than or equal to the absolute value of your n plus 1th derivative at some value t, that value t that's between x and a. And so assuming, or really where t is any value between x and a, sorry. T is anything in between there. It's greater than any of them. So you could, you know, if your values in there never go above 5, you could pick a million, but you're not going to get a very good estimation there. So you'd probably want to say, well, if you can find the exact maximum, like the exact maximum is 5, then you're going to want to use that for m. And so let's do a little example here. Let's look at e to the x here. And we're going to go out to P4 here, where n equals 4. So we'll get 5 terms, n equals 0, 1, 2, 3, and 4. And what we want to do is estimate the value of e to the x at x equals 1/2. Now, if we look here, this here in red, this is e to the x. And then the blue part is going to be our polynomial here that we've come up with. And so let's figure out how good of an estimation this is actually real quick and right here. If you type it into your calculator, e to the 1/2, you should get about, I'm going to have to cut off some decimals, 1.648722127, and then it'll keep going after that, but you get that. So after we look at that, we want to go to the n plus 1 term. So we want to go to the 5th one. So for n equals 5, the next term generated is going to be x to the 5th over the 5 factorial, which would be 120. Okay? Now our error, if we look at this, we can see that, well, one, we just did e to the 1/2 already, 1.648. So what I'm going to do is just, you know, I'm going to pick something. I know that as e to the x goes up, it keeps increasing. So I'm going to pick something that's going to put me above it, but not too far above it. So I'm going to just go with 2. I'm going to let m equals 2. I could probably come up with a better one than that, but I'm going to just kind of pick it. That way I at least know I'm going to be within the error of it. And so, because you know that all the way out to e to the 1/2, e to the 1/2 is actually going to be its maximum. So I guess I could do something like 1.7 if I wanted, or 1.65 or something like that. But I'm just trying to keep it simple. I'm going to pick 2. So our error here, our error function is the absolute value of it at least, right? Error, right? Because this is that leftover part, is going to be less than or equal to, and then I'm going to do 2 times, and we're doing 1/2, so I'm going to plug in 1/2 for the x. I'm using this right here, 1/2 to the 5th over 120. And if you type that into a calculator, or do it out by hand if you really wanted, you should get about 0.005286. And at that point, that gives us a pretty low error. You know, we're 4 decimal places in. And if you look at p to the 4, or p sub 4, going out, n equals 4 of 1/2, and actually plug it in, you get 1 plus 1/2 plus 1/2 squared over 2 plus 1/2 cubed over 3 factorial plus, this was a 2 factorial, but that just equals 2, so sorry about that, plus 1/2 to the 4th over 4 factorial, and you can go through and figure that out, and you get 1.6484,375. So if you see this, according to our error, I mean, we're pretty close. We're within, and that's a pretty big error I did with picking 2, but we've got to be within 4 decimal places, or at least that 5 of 4 decimal places. And you look, 1.648, we're matching, and we don't deviate until the 4th decimal place. So our error is definitely lower than what we came up with right there. And again, you could do a slightly better one. So the rest of the video, it's basically just, here are some common Taylor series. You may want to look at it. Not saying have those memorized. There's a few examples after this. I'm going to go through, fill them out, and then they should back up to the notes for you to look at. And that's about it. If you have any questions, just let me know. Otherwise, I will see y'all later.